Hi, in this video we're going to keep talking about vector functions. Specifically, we're going to talk about their arc length, curvature, and what's known as the TNB frame. But let's start with arc length. So given a curve C defined by a vector function on an interval from alpha to beta, how would we calculate that arc length? So I drew my curve C. The first thing I want you to notice how I put the direction. Remember, anytime we're dealing with a parametric function or a vector function, which is just kind of how we group our parametric functions, we need to make sure that we are paying very close attention to the direction. All right, that is going to become a critical point later on, and it's good practice to start now. Make sure we understand the direction our curves are going. All right. So arc length is going to be the entire length of the curve from alpha to beta, the entire thing. So how do we actually calculate that? Well, it's calculus. We chop it up into a bunch of tiny little pieces. We call those tiny little pieces, well, ds, because big S is the entire arc length. So the little tiny piece, the little tiny chunk is our ds, and we basically want to sum up infinitely many, infinitesimally small, little tiny ds's. So our total arc length, capital S, is equal to the integral of our little ds's. Basically, sum infinitely many of these little tiny chunks together. Now, notice that in this notation, we're integrating over the curve C. And so when we say over the curve C, a lot of times we now use this nice new notation where instead of the bounds of integration, we'll just say C. And it basically lets us write things much neater and more compact and not have to worry about superscripts and subscripts and all kinds of tiny little things. It's just a much nicer way of actually writing things now. And we could even verify that, well, obviously, this definitions make a ton of sense, right? What is the integral of ds? Well, what's the antiderivative of, well, 1, right? What's the antiderivative of 1 with respect to s? The antiderivative of 1 with respect to s is s. Clearly, that's exactly what it should be. But how are we actually going to calculate that practically? Well, that ds, how do I actually find the length of ds? Well, we're going to use our magnitude formula, which is really the same thing as the Pythagorean theorem and the distance formula, and which means that ds is really the square root of the quantity dx squared, the quantity dy squared, and the quantity dz squared. So we substitute that directly into our integral notation, except I can't evaluate this integral anymore because I don't have anything here at the end to tell me what to integrate with respect to. That notation matters. This means we need to reparameterize. And again, we're going to do this in terms of t because, well, my original vector function r was r of t. So my variable is t. So I want in that box at the end to be dt. Well, I can't just magically make that happen. I have to do math. So I'm going to apply the chain rule. Now, all the chain rule really says is that we're introducing some new expression equal to 1 so that we can evaluate our integral. And so again, I want this dt here, this one at the top, so that I can evaluate my integral, which means I need to kind of get rid of this guy. Well, how am I going to get rid of this guy? Well, what I really want to do is, in this case, distribute him through into my square root. I want to actually distribute him into my square root here. Now, the way I'm going to do that, well, 1 over dt is equal to, well, 1 over dt squared under a square root. Distribute that through. And so we get that the arc length, s, equals the integral. Now notice at this point, I am changing back to the limits of integration alpha and beta because that matches the dt at the end. Again, we need to make sure that we're being consistent, and you need to make sure that what's over here on your limits of integration matches the end with what we're integrating with respect to. You have to make sure those things match. All this notation is incredibly important. It's not just there, because Some mathematicians thought it would look kind of fun. All right. So be very, very diligent about your notation. And again, now I'll be able to actually evaluate this entire thing. And this is actually the computational or the practical arc length formula for a curve defined by a vector function, again, each of its components, x, y, and z, and it traverses the curve only once on the interval. There's my formula for arc length. Now, what does it mean if the curve is traversed only once? Well, let's say we have our curve C in space, and we are starting, let's say we start over here. This is alpha. And what we're doing is we're moving along the curve, right? And we have our direction. Direction matters. We're going along our curve. We're going along our curve. But what happens when we get to the end here, the curve actually goes back along the same path in the other direction. And then let's say it goes back along that other path and it stops here at beta. Now, when we calculate the arc length, it's only going to calculate the displacement between here and here. It's not going to calculate this whole back and forth that we traversed on this part. So we need to be really careful. Again, it goes back to making sure that we actually understand what's going on, right? Make sure we understand the vector function. Make sure we've graphed it. Make sure we've denoted the direction. Make sure we've done all of these important steps before we actually start trying to blindly apply calculus and math randomly on our paper. Now, again, admittedly, this might not happen all that often, but it does happen sometimes, particularly when we have anything that has symmetry. So, for example, x squared, right? If we have some quantity squared, there's going to be symmetry, right? It might go from one side to the other. Our trig functions as well. If there's symmetry in there, we need to be very careful that we're only traversing that path once. All right, but let's go back to that vector function. So I had it in, remember, the component form up here, right? R of t, given in each of the components are x, y, and z. The other way we can represent this is with our standard basis. Remember, our standard basis is that I hat, j hat, k hat. And again, that tells us the direction for each of these components, right? The I hat, right? That I hat being the vector 1, 0, 0, right? That standard basis that we were dealing with before. So if I want to find the derivative, right? If I want to go from r to r prime, how do I do that? Well, we take the derivative of each component individually. So x becomes dx, and dt, again, dt because it has to match our variable or our parameter. Y becomes dy, z becomes dz. Now, if I want to find the magnitude of this derivative, well, now we take each of the components, right? We square them, we sum them, and we put them under our radical. So we get, again, dx dt quantity squared plus dy dt quantity squared plus dz dt quantity squared all under my square root. But wait a minute, we just literally saw this exact expression back here in our arc length formula. It's the same exact thing, right? It's the same exact thing, which means I can actually substitute this into my arc length formula. And actually, this gives me a much more compact and kind of conceptual notation for defining arc length. And we're going to actually use this formula quite a bit as we are defining arc length in the upcoming chapter about vector calculus. This formula will absolutely be showing up quite a bit again, because arc length is going to be very, very important when we start talking about these things called line integrals. Now, from what we started with, this simple equation, right? This integral that arc length is equal to the integral over my curve C of all these tiny little ds's, we just showed that this is equal to this same integral as well. Well, if those integrals are the same and we're integrating over the same part, right? Whether I say we're integrating over the curve C or we're integrating from alpha to beta using my curve R, that's the same exact thing. So these limits of integration are actually the same. They're saying the same thing even though we write them slightly differently, which means the integrands must also be equal. That means ds, the integrand of that, must be equal to the integrand of the other one. So ds must be equal to the magnitude of r prime dt. Now, technically, it involves a little bit more rigorous mathematics to actually prove that, but it's really just you got to apply the fundamental theorem of calculus and think of arc length as a function instead so that you can actually integrate. If you want the details, it is in your textbook, page 901. Not as important as just making sure that we understand that relationship right there. We can also take this relationship, divide both sides by dt, and we end up with this other equation that I put in the box, which, to be honest, probably both of these deserve to be in the box. These are both really, really important, and these are also going to show up quite a bit again as we move into the next unit. Because what we're going to be doing with these things called line integrals is we're going to be integrating in space. So either in xy's or in xyz's, but our line integral is going to be one single integral, which means we're going to somehow have to integrate with only one parameter or one variable. And so the most natural place to start is to actually choose arc length and choose ds as that parameter. And how do I relate ds and arc length to, well, a vector function given in terms of t? This is the formula. This is how we're going to do it. This formula will be showing up quite a bit when we first start our unit on line integrals and vector calculus. So please keep that in mind. But now it's time to switch gears a little bit, and we're going to talk about curvature. So before we can really define what curvature is, curvature is only going to make sense if we have what's called a smooth curve. So smooth, your intuitive idea of what it means for a curve to be smooth is exactly right. It's smooth, but we have to be able to define it mathematically as well, right? We need that rigor. And so a curve is going to be smooth if its first derivative is continuous and its first derivative is not the zero vector. All right. And again, if we can verify these two things, we know that our function is going to be smooth, which is good. And it's not going to have any corners or any cusps. And again, why this would be an issue in terms of curvature? Well, let's say I do have a function with a corner, right? This is a corner. Well, what's going to happen if I zoom into that corner, right? The concept of local linearity. Well, the corner is going to look exactly like, well, a corner when I zoom in. And the same thing with a cusp. If I zoom in onto a cusp, it's going to look like a cusp. So again, the whole concept of local linearity is kind of lost there. And so it's not going to make sense to kind of talk about curvature under those conditions. So again, we do need our curve to be smooth. We are going to see that come up, elsewhere as well, that we need smooth curves to do the math. But again, that's how we would verify it. Now, curvature itself, curvature is going to be the measure of basically how curvy our curve is, which is going to be a measure of how fast the curve is changing directions at a particular point. So we define curvature, which is denoted by kappa. I know it looks like a K, but it is technically the Greek letter kappa. And that kappa is going to be the magnitude of the rate of change of our unit tangent vector with respect to arc length. So again, notice curvature is just going to be some sort of scalar number. And what we're going to try to do is actually come up with a scalar function, right? A regular function like f of t, so that we'll be able to find the curvature of our function at any point. Now, we use the unit tangent vector and arc length to define curvature. Now, why does that make sense? Well, we want to use our unit tangent vector, right? And we want to know how fast our unit tangent vector is changing because, well, it has a constant length of 1. It has a constant length of 1, which means I can compare two separate curves relatively using that unit tangent vector. And the example that I'm going to use here is, let's say we had a 6-foot-tall woman talking to a 6-foot-tall man. They're both exactly the same height, right? If you look at the two of them, they have exactly the same height. However, if you were to ask them what it's like being tall, well, the man probably will say, well, I don't feel that tall because a 6-foot-tall man is only about 2 inches taller than average. But a 6-foot-tall woman is at least half of a foot taller than average. So the woman is much taller relatively to the average height of women than the man is. And again, we need a relative frame of reference to be able to compare that and to make sense of it. So in like a statistics course, we use what's called a z-score, which basically is going to compare, well, the man is only a little bit taller than average. The woman is much taller than average. So the woman is relatively taller, even though they have the exact same height. And again, we need that frame of reference, that relative frame of reference, to be able to describe these things. And because we use unit tangents, well, that gives us that relative frame. We know that the unit tangents have to be 1, so we know how they're going to change, right? We also use arc length, right? We do this with respect to arc length and with respect to that ds because we know that arc length is not going to change regardless of how we measure it, right? It doesn't matter how we measure arc length. Any curve in space is going to have that same length regardless of how we measure it. It doesn't matter how we measure it, it'll always have that same length. So it's a great starting place, again, for that relative frame of measure for curvature. Now, how am I actually going to be able to calculate curvature? Well, we're going to apply the chain rule again. And it's the same exact trick that we did before, where I'm basically going to introduce a dt over dt. And the dt over dt, again, goes into our, well, what we had before, d big T over ds. And, well, what's going to happen, though? Well, we know from what we just showed that that denominator, the ds dt, is really the same as the magnitude of r prime of t. So we're going to make that substitution down at the bottom. And then the d big T dt. So the magnitude of, well, d unit tangent vector dt, well, that's just the derivative with respect to t. And my unit tangent vector was already described in terms of t, so dt dt is really t prime. And so again, this is the conceptual, or kind of the main idea formula for how we define curvature. All right, this is what's going on when we actually try to compute curvature. Typically, however, we use what's called the computational, or this more practical formula for curvature. The derivation is on page 905 if you want to actually go through it. I'm more concerned with, can you memorize and use this formula in a practical manner? In the next video that I post, you're going to see I'm going to go through and I'm going to calculate arc length with an actual example, and I'm going to calculate curvature with an actual example. For now, I just want to make sure that this video we have our definitions down. And again, just more notes than examples. But again, this is our computational formula, which is going to involve everything in terms of my original vector function r. So r prime and r double prime. All right. Now, I want to go back. We talked about this before, but let's kind of review. What can I say? What can I deduce if I know that the magnitude of my vector function is a constant? What can I deduce? Well, from the properties of dot products, we know that any vector dotted with itself is its magnitude squared. This is also going to be true for vector functions as well. If it's true for vectors, it's true for vector functions, which means r dot r is really equal to c squared. Now we're going to differentiate both sides. We're going to differentiate the r dot r, and we're going to differentiate the c squared. So for the r dot r, when I differentiate that, well, I'm going to have to use the product rule. It's a product. I need to use the product rule. So that means the derivative of the first, r prime, times the second, r, plus the first, r, times the derivative of the second, r prime. And then, of course, what's the derivative of any constant squared? 0. Now, notice r prime dot r dot r prime. Order doesn't matter with dot products. That means I really have two of them. It's two of the r dot r primes. They equal 0. These are all scalars, right? The dot product gives me a scalar. If I divide by 2, then clearly r dot r prime is equal to 0. And we know from the dot product theorem that if the dot product of two vectors is 0, those vectors must be orthogonal, right? They must form a right angle. So we know that r dot r prime is going to be 0, which means r dot r prime are orthogonal, as long as, again, the magnitude of that is a constant. So, why is that important? Why do I bring it up? Well, we know that by definition, our unit tangent vector has a magnitude of 1, which is clearly a constant. Which means that if I take the derivative, that derivative must be orthogonal to what I started with. So the derivative of my unit tangent, which is t prime is going to be orthogonal to my original unit tangent vector, t. T and t prime are orthogonal. Now, we talked about orthogonal before, and we're going to use the word normal again. Remember before when we were talking about normal, that was when we had that right angle, right? We talked about normal planes. It's always that, what's orthogonal here? And it's the same idea. Now we do want to talk about what's known as the unit normal vector. We want it to have that unit length, just like the tangent vector has the unit length. So we, again, give it that length by dividing by the magnitude of t prime. And this is how we define the unit normal. All right. What this means then is that, again, for some curve C in space, at any point, there's going to be the tangent vector, which is basically telling us the direction that the curve would travel in, right? What's the direction? And then we have our normal vector, which must be at that right angle. All right. So again, we have these two orthogonal vectors at every point along my curve C. Now, time for the next definition, which is our binormal vector. So the binormal vector is the cross product of the unit tangent and the unit normal. Now remember, the cross product means it must be orthogonal to both. So we have this right angle here, right? T and N have a right angle. And then when we take the cross product, this B, well, clearly that must also be at a right angle to my original vectors. So B, the binormal, is orthogonal to both the unit tangent and the unit normal. They're all orthogonal to each other. They form three right angles with each other. Now, the binormal is also going to have a unit length. We can easily verify that with the cross product property because we're taking the cross product of T and N. And so the magnitude of T is 1, right? It's got a unit length by definition. The magnitude of N is also 1 by definition. And then sine of theta. Well, theta is going to be the angle between these two, but that angle between them is a right angle. It's pi over 2, or 90 degrees. So what's sine of pi over 2? What's sine of 90 degrees? It's 1. So what's 1 times 1 times 1? 1, which means the magnitude of the binormal is also a unit length. So these are all unit length vectors that form right angles. And these form a brand new basis for us to describe curves that is very, very useful, particularly with physics. And we're going to use it when I actually do the examples in the next video as well. Again, we're trying to focus most on the concepts with this particular video. And we actually use the TNB, sometimes called the TNB frame, or called the TNB Frame, after some French guys who independently developed it on their own. Again, to do a bunch of physics. Now, again, recall that our standard basis was the I hat, J hat, and K hat, which we had our I hat in the X direction, J hat in the Y direction, and K hat in the Z direction, which again forms our kind of basis for the coordinate plane in space. And those are all at right angles to each other with unit length. This is all right angles to each other with unit length, which again is going to give us a new basis to describe what's going on with physics. All right. Now, this next part of the video, again, doesn't really have much to do with Calculus 3, and you could probably skip it without losing much. But I really want to explain what's going on when we switch our basis like this. And so this is more of an idea that kind of comes from linear algebra, but I think it's worth taking a few moments to just talk about it now as well. So let's talk about it in terms of 2 dimensions because it'll be a little bit easier to see. But again, it should feel completely normal to describe points in a plane using the I hat and the J hat vectors, because that's basically what we've been doing with our rectangular coordinates. So for example, if I have some point in space 3, 2, I can represent this point in space 3, 2 with the vector v being 3i plus 2j. All right, which again should make a lot of sense, right? This vector v would be 3i, and again, I is the vector 1, 0, if we're talking about R2, plus 2j, so 2 times the vector 0, 1. And, well, yeah, if I go ahead and I actually, first distribute, right, my scales, right, distribute my scalars, how big am I scaling this, right? 3 times I becomes the vector 3, 0. 2 times j becomes the vector 0, 2. And when I add those two vectors together, adding the components, 3 plus 0 is 3. 0 plus 2 is 2. And of course, I'm getting back to exactly where I want it to be. Also, we can notice that, again, that vector v is the diagonal of that parallelogram defined by 3i and 2j, right? That's the whole idea of addition, right? When we're adding vectors, we travel the one vector, right? So let's say I travel 3i, then I travel the next vector, 2j, and I'm going to end up at that terminal point. The terminal point in this case being the point 3, 2. And again, that should all feel kind of normal, right? Everything works out the way it's supposed to work out. Everything is good. But this is not the only way that I can get to the point 3, 2. This is not the only way to arrive at that ordered pair 3, 2. So let's say I have a new basis. All right. And let's say my new basis is defined, instead of I hat and J hat, let's define my new basis in terms of A hat and B hat. Now, in this case, we can easily verify that both of these are going to be unit vectors. I'll do it really quick for the magnitude of A. Right, it's the square root of each component squared, so we take the square root of 1/2 quantity squared plus the square root of 1/2 quantity squared. But what's going to happen when I square the square roots? They're going to cancel. They're going to cancel. I'm just left with 1/2 plus 1/2. 1/2 plus 1/2 is 1. The square root of 1 is just 1. Obviously, the magnitude of A is 1. You can easily verify that with B as well. We're also going to be able to verify without too much difficulty that these are also orthogonal. Again, what would we do to show that? Consider A, vector A is the ordered pair xy. B would be the ordered pair x, right? It's the same x component, but negative y. And so you can easily verify that if we have, x equals y and x equals negative y, these are going to be two perpendicular lines, right? These are absolutely going to be two perpendicular lines that would also, I guess, be orthogonal, right? So we have that A hat and B hat are both unit vectors that are orthogonal to each other. Now, I can still arrive at that point in space 3, 2 using these new vectors as my basis. And again, I kind of just gave you the answer, but we can verify that this is absolutely going to be true as well, the same exact way. So the scaling factor for A is root 25 over 2. So root 25 over 2 times my vector A, which is the square root of 1/2, comma, the square root of 1/2, plus, and my scaling factor for B, root 1/2, times, vector B was root 1/2, comma, negative root 1/2. And the same thing we did before. Yeah, we're going to distribute and then add. So when I distribute my scaling factor, root 25 over 2 times root 1 over 2, and multiply the tops, multiply the bottoms. And so I get root 25 times 1. Well, root 25 is just 5. And on the bottom, root 2 times root 2 is root 4, which is just 2. So I get 5 halves, and distributing through, yeah, that's still going to be 5 halves, plus, and when I distribute through this root 1/2, well, root 1/2 times root 1/2 is the square root of 1/4, which is just going to be, well, 1/2. And when I distribute over here, there's a negative, so negative 1/2. And when I add component by component, 5 halves plus 1/2 is 6 halves, which is 3. And 5 halves plus negative 1/2 would be 4 halves, which is 2. And again, I ended up at the same point in space using a completely different basis. And again, it's still going to be the diagonal of this parallelogram that we made in space. And again, the main idea here is that I can use a different basis. Instead of just using I hat and J hat, right? Instead of just using our normal, what we consider our original way of getting to a point, we can actually come up with other bases, right, that get us to that same exact point. So, this should arise, well, hopefully this arises some questions like, well, do they need to be units? If I'm scaling them anyway, right? If I'm scaling each of my vectors, does my basis need to be units, right? If I'm scaling it anyway, and do they have to be orthogonal? Well, these are all linear algebra questions, which we're not going to get into today. Like I said, the next video is going to have more examples of doing arc length and curvature, so you can kind of actually follow through and practice some problems together. Use this video more for the concepts, and send me an email if you have any questions. Thanks.